Welcome to our deep dive into the intricate world of live streaming architecture, a domain where milliseconds matter and scale is paramount. We're going to pull back the curtain on how platforms like YouTube and Twitch manage to deliver real-time content to millions or even billions of concurrent users worldwide. This isn't just about sending video bits. It's about orchestrating a complex symphony of technologies to achieve ultra-low latency, high availability, and an exceptional viewer experience, all while being cost-efficient. For senior software engineers, system architects, and DevOps professionals, understanding these underlying principles is crucial for building robust, scalable, distributed systems. We'll explore the entire lifecycle, from the broadcaster's camera to your screen, uncovering the engineering marvels that make seamless live broadcasts a daily reality across diverse networks and devices. Prepare to explore the core components that handle everything from initial video ingestion to global content delivery and interactive features. The journey of a live stream begins with ingestion, where the raw video and audio from a broadcaster's device are first transmitted to the streaming platform. Most streamers use software like OBS Studio or dedicated hardware encoders, which capture their screen, webcam, and microphone, then encode this raw data into a compressed format. The industry standard for this initial transmission remains Real-Time Messaging Protocol, or RTMP, despite its age. RTMP streams are sent over TCP to an ingest server, which is typically an edge server geographically close to the broadcaster. This proximity is critical to minimize initial latency and ensure a stable connection. Once received, the ingest server performs an initial validation and might slightly repackage the stream, but the primary heavy lifting of re-encoding and preparing for diverse devices comes next. This first step is deceptively simple, yet foundational for the entire streaming pipeline's quality and stability. Once ingested, the single raw stream is far from ready for global distribution. This is where transcoding becomes critical. The ingest stream, often high bitrate and single resolution, needs to be converted into multiple versions or renditions, each with different resolutions, bitrates, and encoding profiles. This process, known as adaptive bitrate streaming, allows viewers to receive the most suitable stream based on their device capabilities and network conditions, dynamically adjusting quality to prevent buffering. Transcoding is computationally intensive, often leveraging GPU acceleration and distributed transcoding farms, converting formats like H.264 or H.265. Each rendition is then segmented into small, fixed-duration chunks, typically 2 to 10 seconds, and indexed with manifest files. This segmentation is fundamental for protocols like HLS and Dash, enabling efficient caching and adaptive delivery. This step ensures that a stream is playable on everything from a 4K TV to a mobile phone on Apache 3G connection. With transcoded and segmented streams ready, the next challenge is delivering them efficiently to millions of viewers worldwide. This is where content delivery networks, or CDNs, play an indispensable role. A CDN is a geographically distributed network of proxy servers and data centers designed to provide high availability and performance by distributing service spatially relative to end users. Instead of viewers fetching content directly from the origin server, which could be thousands of miles away, they retrieve it from the closest CDN point of presence, POP. These POPs cache the video segments, reducing latency and significantly offloading the origin infrastructure. Major platforms like YouTube and Twitch either build their own expansive global CDNs or leverage a hybrid approach with third-party providers. The CDN ensures that content is delivered with minimal delay and maximum reliability even during peak viewership spikes by intelligent routing and load balancing across its distributed infrastructure. While RTMP handles the initial ingestion, delivering the segmented, transcoded video to viewers relies primarily on HTTP-based adaptive streaming protocols, HLS and Dash. HTML live streaming, or HLS, developed by Apple, is widely adopted, especially for iOS devices and browsers. It uses an M3U8 playlist, manifest, to list available renditions and their corresponding TS, MPEG transport stream, or FMP4, fragmented MPEG segments. Dynamic adaptive streaming over HTTP, or DASH, is an ISO standard, offering similar functionality to HLS, but is platform agnostic, supporting a wider range of codecs and container formats. Both protocols utilize standard HTTP infrastructure, making them highly scalable and cacheable by CDNs. These protocols inherently introduce some latency due to segment size and buffering, a trade-off for reliability and compatibility. The choice between HLS and DASH often depends on target platforms, ecosystem preferences, and specific latency requirements, with many platforms supporting both to ensure broad compatibility. While traditional HLS and DASH are excellent for reliability and broad compatibility, their inherent segmentation and buffering introduce several seconds of latency, often 10 to 30 seconds, which is problematic for interactive live events like gaming or Q&A sessions. To address this, platforms employ various strategies to reduce end-to-end latency. Low-latency HLS, LLHLS, and low-latency DASH, LDASH, are emerging standards that reduce segment sizes, use chunked transfer encoding, and introduce partial segment delivery, bringing latency down to 2 to 5 seconds. For even lower latency, often below 1 second, technologies like WebRTC, Web Real-Time Communication, are used, particularly for direct peer-to-peer or server-mediated live interactions, though WebRTC has its own scalability challenges for mass distribution. Custom protocols and optimizations over UDP rather than TCP are also explored for ultra-low latency scenarios, balancing the need for speed with packet loss resilience. The goal is to make the viewer experience as close to real-time as possible, facilitating immediate interaction. Beyond the video stream itself, a crucial element of the live streaming experience, particularly on platforms like Twitch, is real-time interaction. Chat systems are complex distributed applications, operating in parallel to the video delivery pipeline. They rely heavily on technologies like WebSockets for persistent full-duplex communication between viewers and the server, enabling instant message delivery. Messages are typically routed through message queues, e.g. Apache Kafka, RabbitMQ, to handle high message throughput and ensure ordered delivery. Chat servers must manage thousands to millions of concurrent connections, implement robust moderation systems, AI-driven filtering, human moderators, and provide features like emotes, badges, and user-specific permissions. Integrating chat with the video stream, often with a slight delay to synchronize with video latency, creates a cohesive and immersive social experience. This interactivity is what transforms passive viewing into an engaging community experience, driving viewer retention and broadcaster engagement. Building a live streaming platform means designing for massive scale and extreme resilience. These systems are inherently distributed, utilizing stateless microservices wherever possible to allow for horizontal scaling. Load balancers distribute incoming traffic efficiently across clusters of servers, while autoscaling groups dynamically provision or deprovision resources based on demand fluctuations. Data replication and redundancy are critical at every layer, from ingest servers to CDN POPs, ensuring that no single point of failure takes down a stream or the entire service. This involves redundant storage, warm standby servers, and multi-region deployments to guard against localized outages. Health checks and circuit breakers prevent cascading failures, while robust error handling and retry mechanisms maintain system stability. The architecture is a living, breathing entity, constantly adapting to demand spikes, such as a major esports event, and designed to gracefully degrade rather than catastrophically fail, ensuring continuous service for millions. For systems of this scale and complexity, comprehensive monitoring and analytics are not just beneficial, they are absolutely essential. Platforms meticulously track a myriad of metrics to ensure both quality of service, QoS, for the platform itself, and quality of experience, QoE, for the end user. This includes everything from server CPU and memory usage, network latency and throughput, to more specific video metrics like buffering rates, startup times, and stream quality changes on individual viewers' devices. Distributed tracing helps pinpoint bottlenecks across microservices, while centralized logging aggregates data for efficient debugging and incident response. Real-time dashboards provide operational visibility, and sophisticated alerting systems notify engineers of anomalies instantly. Furthermore, analytics drive product development, informing decisions on feature prioritization, infrastructure optimization, and even content recommendation algorithms. This data-driven approach allows for continuous improvement, proactively identifying and resolving issues before they impact a significant number of users, and refining the overall streaming experience. We've journeyed through the intricate layers of live streaming architecture, from initial ingest and intelligent transcoding to global content delivery and interactive chat systems. We've seen how principles of scalability, resilience, and low latency are woven into the fabric of these systems, enabling platforms like YouTube and Twitch to deliver seamless experiences to a global audience. The field is constantly evolving. Expect further innovations in ultra-low latency streaming, with WebRTC potentially playing a larger role for distribution, and even more sophisticated AI-driven content moderation and personalization. Serverless computing and edge processing will continue to optimize infrastructure and reduce operational overhead. The demands for higher quality, lower latency, and richer interactivity will push the boundaries of distributed systems design even further. As senior engineers, understanding these foundational components and future trends is crucial for building the next generation of real-time, high-scale applications. Thank you for joining this deep dive.